What's up? I'm Vin, and I'm going through this exponent and logs practice test, and I'll leave a link to a copy of this test in the description below. So first up here, we have the multiple choice questions, and for question 1, we have the function f of x equals 5 to the x, and we want to know what is f of negative 2. So all we have to do here is just plug in negative 2 to the function. So we're going to replace x with negative 2. So if I have something like 5 to the negative second, when you're dealing with the negative exponent, what you could do is you could find the reciprocal of the base. The reciprocal of 5 is 1 over 5. And then you could change the exponent to a positive power. Okay, so I'm just flipping the base, and I'm going to change the sign of the exponent. So if you want a rule to follow here, when you have something like a to the negative b, you could rewrite this as 1 over a to the b power. Okay, so I could write 1 over a to the b power like this, or I could write it as 1 over a like this to the b power. So here, all we're going to do now is multiply 1/5 times 1/5. I have 1 squared is 1, and then I have 5 squared, or 5 times 5, is 25. So we scan the answer choices, and choice B is going to be our answer. Now, let's say you are allowed to use a calculator for this. What you could also do is press 5, and you're going to press the exponent button here, and you could type in negative 2. And when you type this in, you get 0.04. And if you have the TI 84 plus CE, from here, what you could do is just press math, enter, enter to turn this into a fraction. And you'll see that this does match with 1 over 25. So choice B is definitely our answer. Question 2, we want to know what is the domain of the log function g of x equals log base 2 of x plus 3. So for something like this, if you're doing this no calculator, you should know that the inside of a log function has to be positive. It has to be greater than 0. So just knowing that, if we set x plus 3 to be greater than 0 and solve for x, we're going to get x is greater than negative 3. We just solve this by subtracting 3 on both sides. And 3 minus 3 cancels, and we have x is greater than 0 minus 3 is negative 3, so we get choice A. Now, we could also use technology to help us understand this. We could go to the y equals, and we could type in log base 2 by pressing math. We go up, and log base is option A here, so I just go up to option A. I press log base, and I can write log base 2 of x plus 3, and I could press graph. So once I do this, I get an idea of what this looks like, and notice that the graph ends over here at negative 3. So the graph exists for all values of x where x is greater than negative 3. If we press second graph and go to the table, notice that once we get to negative 3, this is where the error is, and we have no values less than negative 3 for the function that work here. Okay, and that's once again because the inside of the log function has to be positive. It can't be 0 and it can't be negative. So here, notice choice B. Choice B is a very dangerous bear trap, okay? The equal to is tempting, but what you could do if you're unsure is just look at the table and notice that if you were to plug in negative 3, you would get log base 2 of negative 3 plus 3 is 0, and we cannot have a 0 inside of a log. We can only have positives. So that's why choice A is our answer. Question 3, if log base A of B equals C, which of the following is the exponential form? So for a question like this, you could just use the loop. The loop is you start here at the base and you go around like this. You're going to go from here, from A to C, and then back to B like this. And then when you write the exponential form, it's A to the C power equals B. If you just want to know what each of these terms mean, then what you could do is just know the definition of the log, that the subscript over here is the base of the log. So this is the base. This would be the exponent, and then this would be the result over here. So if we want to go from log to exponent form, the base is A, the exponent is C, and the result is equal to B, and we could just match this up with choice A. Question 4, what is the value of 7 to the 2 times log base 7 of 5 power? So for this one here, it really helps to know this idea that when you have something like a to the log base a of b power like this, a to the log base a are inverse or opposite operations, and they just cancel out and they send you right to the value b like this. The problem with this expression though is that there is a 2 in front. There is not a 1 in front. The invisible number in front of this log is 1. So it could only use this idea when we have a leading 1 in front. So what I want to do first is use this property of logs, that when you have something like c times log base a of b, what you could do with that coefficient is you could send it back inside the log as an exponent. So I could write this as log base a of b to the c power. I could send this back in. So that's what I want to do first up top is I'm going to send the 2 in front of the log inside as a power. So I'm going to rewrite this as 7 to the log base 7 of 5 to the second power. So I'm sending that 2 inside the log as an exponent. And now this would simplify as 7 to the log base 7. And then we have 5 to the second power is 25. And now I could use this inverse idea that 7 and log base 7 are inverse functions. They are opposites. They cancel out nicely. And we're left with 25. So our solution here is choice C. But if we get to use a calculator, that makes this question much easier. But it does take all the fun away. So we could write 7 to the power, and then we have 2. Log base 7, I'm going to press math. I'm going to go up to option A, and I have log base 7 of 5. So I'm just typing in exactly what I see in the question. And notice that this simplifies to 25. So choice C is definitely our answer. Question 5, use properties of logs to rewrite this expression as a single log. So for this question, it really helps to know properties of logs. And the properties that we need to know are if we have something like log A plus log B, we can combine this to a single log by writing this as log of AB. Okay, so when you have addition of logs, you can combine the logs into a single one by multiplying their inside terms. But just know you could only do this when the logs have the same base. Now, you might be thinking, wait, there's no base written here. But just know if there's no base written there, there is an invisible 10. Okay, so there is an invisible 10, and that number is just implied to be there when all we say is log. The same way when you have a square root and there's no number written there, the invisible number is a 2. This is kind of the same idea notation-wise when we're talking about logs. Okay, and then when we have something like log A minus log B, subtraction of logs with the same base, you can combine by dividing the inside terms. Okay, so we have log of A over B. And I'll just throw parentheses here to show we have a single log here, log of AB. And then when I have a power inside, if I have log of A to the B power, I could write this as B times log A. So powers could come out as coefficients. So these are the 3 big properties of logs that you need to know. And just know this also applies if I had something like, let's say, log base 7 of A plus log base 7 of B, then I would have log base 7 of A times B. So this applies to any logs that have the same base. So from here, what I want to do is I want to apply the properties to simplify these logs and eventually squeeze them to a single log. So when you're trying to combine the logs into a single log, you usually want to look for the third property here, because in order to start combining logs, we can't have any coefficients in front of the logs other than 1. So the ones that I'm noticing right away here are this log over here and this log over here. They have coefficients of 1/3 and 2. So I'm going to send in those coefficients as exponents. So we're going to have log of A squared, and then we're going to have plus log of B to the 1/3 power, and then we're going to have minus log of C to the second power. Okay, so this is the first property that I want to use, and I'm doing that so that we have coefficients of 1 in front of all of these. Now, looking at the answer choices, I noticed that there are no rational exponents. So what they're doing is they're turning the rational exponents into radical form. So the next idea that we need to know is that when I have something like A to the B over C, this is power over root. I could write as C, the C root of A to the B power. Okay, so the power and the root go in these places here. We put the root in front of the radical and the power inside like this. So that's how I'm going to deal with this term over here. We have log of A squared plus I have my power 1 and my root 3. So I'm going to have log of the cube root of B. And I can write B to the first power, but B to the first power is not that exciting. That number doesn't really add much value here. So I'm just going to leave it out. So when there's no power written, the invisible power is 1. And then we have minus log of C squared. So then next what I want to do is use that first property of logs. I'm going to combine these two logs here by multiplying their inside terms. So we're going to have log of, and then we have inside here A squared times the cube root of B. Okay, so all I'm doing here is on these first two terms here, I'm applying that first property of logs. and I still have the minus log of c squared. And now finally, I can combine these into a single log. I'm going to say next that we have log of, and since we have subtraction, now we're going to use that second property. I'm going to write the inside of the first log in the numerator. So we have a squared times the cube root of b. And then in the denominator, I'm going to write the inside of this log, which is c squared. And now I just scan the answer choices here to see which one has the matching term on the inside. So we have a squared, which will eliminate this choice, but a squared times cube root b over c squared. So our solution here is choice A. Question 6, what is the asymptote of the function f of x? And for this question, if we want to do this without a calculator, we should think of what the graph of e to the x looks like. So if we look at e to the x, the exponential function, the asymptote of this function is the x-axis, which has the equation y equals 0. Okay, so I'm just thinking about this part of the graph over here. So we would be dealing with a horizontal asymptote. So this function here is a translation of e to the x. So that means that the asymptote is going to be in the form of y equals. So right away, I'm just going to chop out these two answer choices. And now notice that we're going x minus 2, which is going to take this graph here and shift it to the right 2 units. So it's going to go 1, 2 to the right, and then it's going to go up 3 units. It's going to go up 1, 2, 3. So if we think about where the previous asymptote was, it was at y equals 0. So when we shift the graph up 3 units, the asymptote is going to move to y equals 3. So choice A would be our answer. One thing we could do to check our answer is just graph this function. So we have e is second and then natural log, and then we have x minus 2 in the exponent spot. And then we get out of there and we write our plus 3. And now I'm going to press graph, and here's our exponential curve. And if I write in y equals 3 right under it, notice that this would act as our horizontal asymptote. The problem with y equals 0 is that this line is just too low, and the graph is not approaching this line over time. It's approaching the red line here. So choice A is definitely our answer. Question 7, the population P of a city increases by 2.5% each year. If the current population is P naught, which function represents the population after T years? So for this one here, what we should know is when we're dealing with this type of population growth here, we're going to be dealing with this formula. We have A equals, and then we have P times 1 plus or minus R, but in this case, we're dealing with population growth. The population is increasing. So we're going to have 1 plus R and then to the T power. So here, all we have to do is deal with the initial population is P naught. So we're going to have here P of T is equal to the initial population, once again, is P naught, and then we have 1 plus R is the interest rate expressed as a decimal. So I would have R equals 2.5% is 2.5 out of 100. And this simplifies to 0.025. So I would just write in here, we're going to have 1 plus 0.025 to the power T. And now we just simplify this here. And this is going to give us P of T is equal to, and we have P naught times 1.025 to the T power. And this matches up with choice A. Question 8, we need to simplify this expression. And it's very important to know this property here. When we have e to the natural log x power, e and natural log are opposites and they cancel out. So e to the natural log x is just equal to x. And we could also say that natural log of e to the x is equal to x because once again, natural log and e are opposites and they just cancel each other out. So we could use that idea to answer this question here. E and natural log are opposites. So this simplifies to 4 plus, and once again, we're going to use the idea that e and natural log are opposites, and that's going to give us 4 plus 9. And 4 plus 9 is equal to 13. So choice B is our answer. But for this one, we could also just use the calculator. We could press second E, and then we're going to write e to the natural log 4. And I'm going to get out of this exponent, and I'm going to write plus, and I'm going to do second natural log again, and I'm going to write e to the natural log 9. So we're going to press natural log and 9, and then we just press enter, and this simplifies to 13. So choice B is definitely correct. Question 9, we're going to solve this equation here, and I want to do this algebraically. So we have 3 to the 2x plus 1 equals 81, and 81 I'm going to express as a power of 3. And if you don't have that power just, on the ready, what you could do is you could rewrite 81 as 9 times 9, and then note here that 9 is equal to 3 to the second power. So now we could rewrite this as 3 to the second power times 3 to the second power, which is equal to 3 to the 4th power. So we're just doing the prime factorization here of 81. And that allows us now to set up this equation here. We have this expression on the left equals 3 to the 4th power. But with exponential equations, anytime you have an exponential equation where you have some power on the left equals some power on the right and the bases are the same, you can set the exponents equal to each other, okay? And once again, we could only do this because the bases now match. So now what I'm going to do here is set 2x plus 1 equal to 4 and solve for x. So we're going to go minus 1 on both sides. And on the left side, 1 minus 1 cancels, and we get 2x equals 4 minus 1 is 3, and then we divide both sides by 2, and this will give us our solution. We're going to have x equals 3 over 2, so choice C is our answer. Question 10, if the half-life of a substance is 8 years, which function models the amount remaining from an initial quantity Q after t years? So for this one, what I want to do is make a table of values, and we're going to have the t column and the a of t column. And at time 0, we're going to have a quantity of Q, because at time 0, that's the initial time, and we're told here that we have a quantity of Q. And then 8 years goes by, and that's our half-life. After 8 years goes by, we're going to have half of the substance remaining from the amount we're looking at. So if we're starting out with a amount of Q, then we're going to have Q divided by 2 remaining after 8 years. And then another 8 years goes by. That's going to bring us to 16 years. And we're going to have half of Q over 2. So I could take Q over 2 and multiply by a half, and that's going to bring us to Q over 4. So then what I have to do here is just plug in these values of t into the answer choices and see which one gives us these matching values here in the a of t column. So right away, I could see choice A is good, because if I plug in, let's say, t equals 0, that would give us, we'd have a of 0 equals, we have Q times 1/2 to the 0 divided by 8 is 0, and 1/2 to the 0 is 1. So that gives us Q times 1, which is equal to Q. But for the remaining answer choices here, if I plugged in 0 for t, notice that I would have 1/2 to the 0 is 1 times Q, and that would not eliminate choice B. And same thing if I plugged in, actually these here, if I plugged in 0, this would give me 2 times Q is 2Q. So right away, I could see that choice D is definitely no good. Okay, so choice D is out. And if I plug in 0 for t here, we have division by 0, and dividing by 0 is undefined. So C is also out. But now let's look at this answer choice over here. What is wrong with choice B? Well, let's say I were to plug in 8 into choice B. So I'm going to plug in t equals 8 into choice B. So I have, let's say here, a of 8. And that's going to give us, we're going to have Q times, and we have 1/2 to the 8 times 8 is 64. And what that would do after 8 years, that would multiply by 1/2 64 times. So that would significantly reduce the amount of substance here. So that's why this answer choice here is no good. But watch what happens if we plug in t equals 8 into choice A. We would have a of 8 is equal to, and then we have Q times 1/2 to the 8 divided by 8. And now we're going to have, this is Q times 1/2 to the first. And if I do 1/2 times Q, that gives me Q divided by 2. And plugging in t equals 16 is going to give me Q over 4. So choice A is definitely good. Question 11, we'll solve this by converting this log equation into exponent form. So we have log base 5 of x plus 2 is equal to 3. And for this one here, we have to know that 5 is the base of the exponent. So we're going 5 and then to the power 3 is equal to the inside of the log here is equal to x plus 2. Okay, so just knowing how to go from log form to exponent form is very helpful. This subscript here is the base of the log. Okay, so it's the base of the log, and that becomes the base of our exponent. The term here after the equal sign is the exponent, and the result goes inside the log. Okay, so this says 5 to the third equals x plus 2. And now 5 times 5 times 5 is 125. We set this equal to x plus 2, and now some simple algebra here. We just subtract 2 on both sides, and this tells us that 123 is equal to x. Choice B is our answer. Question 12, Sarah invests $1,000 in a savings account with an annual interest rate of 4% compounded semi-annually. Which of the following functions represents the amount A of t in dollars that Sarah will have in the account after t years? So for this one here, we have to know this formula. A equals P times 1 plus R over N to the NT power. And the difference between this formula and the formula I used earlier, where I had P times 1 plus R to the T power, is this new term here, N. So let me just actually not erase. We're going to highlight instead. So we're looking at the term N here. And this represents the number of times the amount is compounded per year. So if we're compounding semi-annually, semi means twice a year. Okay, so it's going to happen halfway through the year, and it's going to happen at the end of the year. So this tells us that N is equal to 2. Sarah is investing $1,000, so that's a p-value of 1,000, and the interest rate is 4%. So R equals 4% is 4 out of 100, and as a decimal, this is 0.04. And which of the following functions represents the amount A of t? Well, for this, now we just plug into the formula. We're going to have A of t equals 1,000. And then we have 1 plus R is 0.04. And we are dividing by 2. And we're raising this to the NT power, so to the 2t power. And now just scanning through the answer choices here, we can see that this is going to be choice B. Choice A is tempting, but what's wrong with choice A is this answer does not take into account the fact that the money in the account is going to be compounding semi-annually. Okay, that part is ignored. That's why A is no good. This would be true if we were compounding continuously, and this would be if the amount of money in the account was decaying. Okay, we have an annual interest rate, which means the money is going to be growing. It's not going to be shrinking. So D is out. B is our answer. Question 13, the population of a certain species of fish in a lake is modeled by the function P of t, where P of t is the number of fish after t years, and the initial population at time t equals 0 is 200 fish. Approximately how long will it take for the population to reach 1272? So for this one, we could just type this function into the calculator. We have 200, and then we have e is second natural log, and we're raising e to the power 0.05 times t. And in place of t, we're going to use x. And we want to know, when is the population going to reach 1272? So we could just scroll in the calculator, but what we could do here is just type in the value that we want the function to reach. We press graph, and then we think, oh no, I can't see anything. But what we do is we go to the y maximum, and we raise it up so that we could see 1272. So maybe I'll raise this up to 1500. And then I look at the answer choices, and the biggest answer choice is 37. So I'll bring the x maximum out to 45, so that way it covers all of the answers. And now we can see we have a nice point of intersection here. I'm going to press second trace 5. I'm going to go up to that point of intersection and press enter 3 times. So we have 1, 2, 3. And this tells us our point of intersection is at 37 point. We have 3 zeros and a 5. So choice D is looking like our answer. Now, one thing I want to point out is that this value here is really representing the t value, which is the number of years that goes by. So after 37 years, the population of fish is going to reach 1272. So our best answer here is going to be choice D. Question 14, we're going to expand this log expression. And what we could do first is use the subtraction property. We have division on the inside. Notice we have this nice fraction here. So we could separate this log into 2 logs by writing log base b of, we're going to have cube root of x squared y. And then I'm just going to close this bracket, and we're going to have minus log base b of the denominator is z to the 4th. So we have z to the 4th. And now from here, what I want to do is I want to rewrite this radical in rational exponent form. So I have x squared y, and just think of this as x squared y to the 1st, so that in the next line we could write log base b of, and then we have on the inside here, we're going to have x squared y to the power over root. So the power of x squared y is 1 over the root of the radical is 3. So we have this, and now minus log base b of z to the 4th power. And then from here, we're going to use the exponent property. So notice that we have these exponent terms here inside of the logs. So those we could bring to the front of the logs, and we could write 1/3 times log base b of, we have x squared y. So now I'm just going to write x squared y like this. And then I have minus log base b of z to the 4th. but I'm going to bring that 4 inside of that log to the front. Okay, so we're going to have, I'm just going to write over here, the 4, and then we have log base b of z. So then from this step, what we're going to do is apply the sum property to this log. Notice we have multiplication on the inside. We have x squared times y. So I'm going to apply that property. I'll write it over here. We're going to have 1/3, and now we have log base b of x squared plus log base b of y. And then we have minus 4 log base b of z. But just to save space here, what I want to do is that power 2, I'm going to use the exponent property and bring it to the front. So we're going to take this 2 here and we're going to move it to the front. We're going to write it as a coefficient. And now the last thing I'll do is distribute the 1/3. And let's just see here. Do they distribute the 1/3? It looks like the 1/3 is distributed. You can see choice A is looking like our answer. So I have 1/3 times 2. So let's just clean that up a bit. We have 1/3 times 2. That's going to give us 2/3. We have log base b of x. And then we have plus 1/3 times the invisible 1 in front is 1/3. And then we have log base b of y. And then we have minus 4 log base b of z. So our answer here matches up with choice A. Question 15, we want to know the solution to this equation here. So we have 10 to the x plus 2. And what I want to do here is get matching bases on both sides. So I have 1 over 1,000 is the same thing as 10 to the 3rd power, because 10 times 10 times 10 is 1,000. And now I want to get this to say 10 to some power on this side here. So I'm going to write instead, we have 10 to the x plus 2 is equal to, and 1 over 10 to the 3rd, I could write as 10 to the negative 3rd like this. So now what we have is we have an equation where the bases are the same on the left and right side. So all we have to do is just set the exponents equal to each other. So we're going to set x plus 2 equal to negative 3. And now we just do a little algebra here. We subtract 2 on both sides, and this gives us x equals negative 5. So choice D is our answer. Question 16, we're going to solve this log equation for x. So we have 2 logs that have the same base. If there's no base written there, the invisible base is 10. So now we could apply the properties of logs since we have 2 logs with the same base. So I'm going to combine these logs by saying log of x times x minus 3. Remember, when you have 2 logs that have the same base and they're attached by addition, you can combine them by multiplying the inside terms. And now this is all equal to 1. So now we clean this up a bit. We have we have x times x is x squared. And then we have x times negative 3 is minus 3x. And this is all equal to 1. So now what I want to do is I want to go from log form to exponent form. So the invisible base here is 10. So I would have 10 to the 1st power is equal to x squared minus 3x. So I could say x squared minus 3x is equal to 10 to the 1st power. So now that I've gotten rid of the log, I could solve this resulting quadratic equation. So I'm going to go minus 10 on both sides. And now from here, we're going to have x squared minus 3x minus 10 is equal to 0. So now to solve this equation, we're looking for 2 numbers that have a sum of negative 3, and the 2 numbers also have to have a product of negative 10. So that's going to give us x minus 5 times x plus 2. And we're setting this equal to 0. So now we just solve the resulting equation, and we're going to have from the first factor here, this gives us a root of x equals 5. When we set x minus 5 equal to 0, the solution here is x equals 5. And if we set the second factor equal to 0, this is going to give us a solution of x equals negative 2. So we have 2 solutions. No, this is a very dangerous bear trap. You have to make sure to check your answer for a question like this. So we have to plug this back into the original log equation just to make sure that it stays in the domain of this part here. So if I plug in x equals 5, I have log of 5 plus log of, if I do 5 minus 3, I get 2 equals 1. And for this one, if I apply the properties of logs, I'm going to get log of 5 times 2 is 10. So I can go that route and really go forward here, or I could just plug this into the calculator to verify. So we're back on the main screen. I'm going to press log 5, close the parentheses, and write plus log 2. And let's see if this works out. And we do get 1. So this equation checks out here. And now if I were to plug in x equals -2, x equals -2 is going to give me log of -2. And then plus log of -2 minus 3 is -5 equals +1. But right away, we have to reject this. This is not valid because we cannot have log of a negative, okay? The inside of a log has to be positive here. So this one here is no good. We have to reject this solution here, okay? So we could cross this one out and say that x equals 5 is our only solution. Question 17, we have f of x, and we want to find the value of x for which f of x plus 1 is equal to 16. So for this one, we're going to take our function f of x, and in place of x, we're going to write x plus 1. So we have f of x plus 1 is equal to 2 to the x plus 1 power. And then from here, we're trying to find out which value of x is going to give us f of x plus 1 equals 16. So now I'm going to set this, the 2x plus 1, equal to 16, and then I'll just do the algebra. So what we could do here is we could rewrite 16 as a power of 2. And 16 is 2 to the 4th power. So we could say 2 to the x plus 1 is equal to 2 to the 4th power. And the only way this equation is going to hold true, we're going to have to set the exponents equal to each other because we have matching bases, which means that the exponents have to match. So now we'll just solve this. We have x plus 1 is equal to 4. And after subtracting 1 on both sides, we're going to get x equals 3. And this is our solution to 17. Question 18, we're going to graph the function f of x on the set of axes below. So let's type this in. We have negative log base 2. So I'm going to press math and go up to log base. And we have log base 2. We hit the right arrow to go inside the parentheses. And now I'm going to type x plus 4, hit the right arrow to get out, and then tack on plus 3. And I press graph, and notice that we could see a piece of the graph. This part of the graph over here is actually heading towards a vertical asymptote. All right, the calculator is not perfect. It's not able to show the dotted line here that this graph is approaching, but that's the concept of a log function, okay, that it has a vertical asymptote. And for precision, I'm going to press second graph and go to the table here, and I'm going to copy down the values where we have integer y values. I don't want to use these decimal values here when I'm making the graph. And notice that when we get to -4, we get an error in the y column here. And this is suggesting that our domain is going to be starting somewhere in the neighborhood of -4, but we'll talk about how to get something precise for part B. So now we'll just copy down the significant points from the table. I'll plot the points and connect them. So one thing to point out is that at x equals -4, we have a vertical asymptote. Now, how do we know that the vertical asymptote is at x equals -4? Well, notice that the error in the table occurs at x equals -4, but the true giveaway here is the inside of the log, okay, this part over here. When you're looking for the domain of a log function, you want to set the inside part to be positive. So we want to set x plus 4 to be greater than 0. So when we solve for x, in this case here, we do -4 on both sides. This is going to give us the domain, but it's also going to tell us where the vertical asymptote is. So once I solve here, 4 minus 4 cancels. I have x is greater than -4. So this is the domain of f of x. But note here that we have x is greater than -4. The location of our vertical asymptote is at x equals -4. So when I have a linear piece inside the log like this, I just set the linear piece equal to 0. I do that math in my head, and then that tells me where the vertical asymptote is. So for the last part of this question, what is the equation of the asymptote of f of x? We have a vertical asymptote at x equals -4. Question 19, Frank invests $8,800 in an account that earns 5% interest compounded continuously. Hank invests $8,850 in an account that earns 5% interest compounded quarterly. And for part A, we're going to write a function for f of t and h of t, where f of t and h of t tell us how much Frank and Hank have in their accounts after t years. So let's look at the accounts first. So we're talking about compounding continuously and compounding quarterly. So for the continuous one here, we're going to use the formula apert. So I say apert because it helps you remember the actual formula, and it's a equals pe to the RT power. And then the formula we're going to use for Hanks function is we're going to use a equals p times 1 plus r divided by n to the nt power. So when we're setting up the function for Frank's account in part A, we're going to use that first formula here. We have capital F of t is equal to, capital P is the amount of money that Frank invests. So that's going to be 8,800. And then we have e to the power r times t. And we're talking about 5% interest. So that's r equals 5%, which is 5 out of 100. And as a decimal, that's 0.05. So I'm going to write the power 0.05t. And then for Hanks function, we'll call that h of t. We're using this second formula here. Okay, I'll just make that a little bit neater. So we have h of t equals, capital P is 8,850. So Hank is starting off with more money. And we have 1 plus, the interest rate is 0.05. And we are dividing by, well, let's see, how many times, n represents the number of times the account compounds per year. So if it's compounding quarterly, that means 4 times per year. That's n equals 4. Just think there's 4 quarters to a dollar, okay? But a quarter just means breaking it into fourths. You could think there's 4 quarts in a gallon, but that's the idea. We're going with n equals 4. So we have 1 plus 0.05 divided by 4, then to the power 4t. And for this one here, we could just simplify this. So if we want to simplify the inside here, we're going to say now h of t is equal to, we have 8,850 times, we have 1.0125 to the 4t power. Okay, so all I did was just type in the calculator 0.05 divided by 4 and then add it to 1. So here are the two functions. So next we're going to algebraically solve for the time t when Frank and Hank have the same amount of money in their accounts and we're rounding to the nearest hundredth. So what we're going to do is just set these two equations equal to each other. So we're doing, for part B, we're doing 8,800 and then we have e to the 0.05t. And we're setting this equal to, we have 8,850 and then times 1.0125 to the 4t power. So this equation here is a little tricky to solve, but what I would do first is get the constants to one side. So the 8,800 and the 8,850, I'm going to put them on one side of the equal sign. So I'm going to divide both sides first by 8,800. So we'll just write out, we have 8,800. We're dividing on both sides. And on the left side, we have 8,800 over 8,800 canceling out. And this is going to leave us with, we have e to the 0.05 times t. And for this one, I could just cross off trailing zeros. And now we have 885 over 880. And then we have times 1.0125 to the 4t power. And then from this step, what I'm going to do is take the natural log of both sides. So I'm going to take the natural log of the left and the right side. Now, just know that natural log and e are opposites. So these terms here are going to cancel. And this will bring us to the next line where we have 0.05 times t. And now this is equal to, we have this whole mess. But one thing I want to point out here is that it's 885 over 880 times this expression here. So I'm going to use the property of logs that when we have multiplication inside of a log, we could split the log by addition. So I have ln of 885 over 880. And then I'm going to write plus natural log of 1.0125. And I'll put another set of parentheses here to the 4t power. Okay, and our goal is to solve for t. So what I'm going to do with this is I'm going to bring the 4t out using the exponent property of logs. We have an exponent inside of the log, so I'm going to bring it in front and attach it by multiplication. So in the next line, we're going to have 0.05t equals, and then we have natural log of 885 over 880, and then plus, I'm going to bring this in front, we have 4t times natural log of 1.0125. Okay, and now this algebra definitely gets a little bit tricky, but what you want to do from here is get the t terms on one side of the equal sign. So these terms here belong on one side. So I'm going to subtract this to the other side. I'm going to subtract 4t natural log of 1.0125. Okay, that's going to be subtracted on the left and the right side. So let's see what we get here. So I know this is quite a bit of work, but the question did say algebraically, so we're going to just do all this, all this stuff here. So now I have 0.05t minus 4t times natural log of 1.0125. And this is equal to, we have natural log of 885 over 880. And from here, notice that we have a common factor of t. So now I could factor this out. So let's write this out. We have t times 0.05 minus, and we're left with 4 times natural log of 1.0125. So just notice that t was the only factor that was brought out. So I'm leaving the 4 and the natural log behind. And then I close the parentheses. And this equals natural log of 885 over 880. So from here, all we have to do is divide by this factor. So we're dividing by 0.05 minus 4 times natural log of 1.0125. And we're doing this on both sides. Okay, so we're going to divide this side by 0.05 minus 4 natural log of 1.0125. And the rest we just type in the calculator. So just to make sure I type this in nicely, I'm going to press alpha y equals enter to pull up a blank fraction. And then we have natural log of 885 divided by 880. I close the parentheses, we go to the denominator, and then we have 0.05 minus 4 times natural log of 1.0125. Okay, just press enter, and here's our solution. But for this question, remember, they told us to round to the nearest hundredth. So we looked at the hundredth place is an 8, and to the right is a 1. So we're going to round this down to 18.28. Question 20, our last question. We have a freshly brewed cup of coffee, has a temperature of 95 degrees Celsius, and is placed in a room that maintains a constant temperature of 20 degrees Celsius. To model the cooling of the coffee, we can use the function C of t, and we have this function here, where C of t is the temperature of the coffee at time t in minutes. C sub r is the constant room temperature. C sub 0 is the initial temperature of the coffee, and K is the positive constant that represents the cooling rate. So for part A, after 5 minutes, the temperature of the coffee has dropped to 80 degrees Celsius, and we need to use this information to solve for K. So for questions like this, I really take my time setting them up. So what I do is I go on a scavenger hunt to see what are each of these pieces in the equation. So C sub R, I just look in the question. C sub R is the constant room temperature. So the constant room temperature, if we look in the beginning of the question, is 20 degrees Celsius. Okay, so this is, I'm just going to say 20 here because we're going to set up the formula in a moment. So we have C sub R equals 20. The next thing that we have to be able to plug in is C sub 0. C sub 0 is the initial temperature of the coffee. So a freshly brewed means it was just brewed. Cup of coffee has a temperature of 95 degrees Celsius. So that's going to be the initial temperature of the coffee. So that's the next thing that we find. And K is the positive constant, and we're going to solve for K when we're answering part A. So from here, now we could set up our formula. So we have C of t equals, and we have C sub R is 20 plus, now we have C sub 0 is 95 minus C sub R is still 20, and this is going to be multiplied by e to the negative kt. Okay, so far what we have C of t is equal to 20 plus 95 minus 20 is 75, so we have 75e to the negative kt. But what they're telling us here, after 5 minutes, the temperature of the coffee has dropped to 80 degrees Celsius. That tells us that C of 5, so t is measured in minutes here based on the question, that C of 5 is equal to 80. Okay, because once again, 5 minutes goes by, the temperature of the coffee has dropped to 80 degrees Celsius. So this information we're going to use, and that's going to help us solve for K. So C of 5, if I plug in T equals 5 here, that's where I'm getting C of 5 from. I'm going to have C of 5 equals 20 plus 75 times e to the negative k times t is equal to 5. So I have negative k times 5. And all of this is equal to 80. So now all we have to do is just do the algebra and solve for k. So I have this equation here. I'll just write it separately. We have 20 plus 75 times e to the negative 5k, and this is all equal to 80. So now here's the algebra. We're going to go minus 20 on both sides. And on the left side, 20 minus 20 cancels. We have 75 times e to the negative 5k is equal to 80 minus 20 is 60. And then from here, we could divide both sides by 75. I could leave this fraction on the right side unsimplified, but I notice here that 60 and 75 are both divisible by 15. So I'd rather simplify this and say, I'll write it over here, e to the negative 5k is equal to 4 over 5. Okay, I'm just dividing the top and bottom here of this fraction by 15. And now to get k alone, I'm going to do the opposite of e as natural log. So we're going to take the natural log of both sides, and then natural log and e cancel out. So these terms are going to cancel, and we're going to have negative 5k equals natural log of 4/5. And then from here, we're just going to divide both sides by negative 5. All right, so here we're dividing by negative 5, and the question said to solve for k. They didn't tell us to round. So I'm going to leave k as is. I'm going to leave it in this form here. And one thing that I'll do is instead of saying divided by negative 5, I'm just going to say negative 1/5 times natural log of 4 over 5. Okay, so just note dividing by negative 5 is the same thing as multiplying by negative 1/5. So here is our k value. So now for part B, find the time t to the nearest hundredth when the coffee's temperature is 50 degrees Celsius. So for this one, what we're going to do is we're going to take the function c of t, and we're going to plug in the k value that we found in part A. So now we'll have a complete function for c of t. We have c of t is equal to 20 plus 75 times e to the negative k, and k is negative 1/5 times natural log of 4/5. And then all of this is being multiplied by t. So I'll simplify this a little bit because we have a negative times a negative here is a positive. So I'm just going to rewrite c of t a little bit more simplified. We have c of t is equal to 20 plus 75 times e to the positive, and now we have 1/5 natural log of 4/5, and then all of this times t. Now remember, our goal here was to find when the temperature of the coffee goes to 50 degrees Celsius. So we weren't told to do this question algebraically, so I'm going to use technology for this one. So I'm going to go over to the y equals, and we'll type in the function. We have 20 plus 75 times e is second natural log, and now we have 1/5. So for this one, I'll just press alpha y equals enter to pull up the fraction, and we have 1 over 5. And I press the right arrow, and then I have natural log of 4/5. I close the parentheses, and then I tack on my variable like this. In the second line, I'm going to put 50 because we want to know when is the temperature going to 50. So we press graph, and we think, oh no, I can't see anything. And that's because we're looking for when does the graph reach a height of 50. So at the very least, I need my graph to go up to 50, but I'll go up to, let's say, 75 so that I can see what's going on. So we press graph, and now we could see more of what's happening. But notice that I need to go more in this direction here. So maybe what I'll do is I'll bump my x maximum out to 50, and I'll make my y maximum even higher. Maybe I'll make this go up to 100. And let's see what we got. So there it is. Okay, we have our point of intersection here. I'm going to press second trace number 5 and press enter 3 times. Okay, and this tells us the time when the temperature of the coffee goes to 50 degrees Celsius. Now, if you're using technology to answer the question, I would sketch this out on your paper. I would label this part here C of t, and I would call this one over here the line y equals 50. And then I would point out that we have an intersection point here at 20.531419, comma 50. And then when they ask for the solution, when is the temperature of the coffee equal to 50 degrees Celsius? And we are rounding here to the nearest hundredth. Then I would just take this over here and I would round the x value, or in this case, the t value, to the nearest hundredth. Okay, so we look to the 3 in the hundredths place, to the right is a 1. So we're going to round down to 20.53. Okay, so we're saying at t equals 20.53, this is our solution to the last question.